Deep dive, you know how this works, right? You send us the stuff you're curious about, and we dive deep. We break it down, pull out the good stuff, the really interesting bits, and try to make sense of it all.
It's like a knowledge distillation process, right? Taking those dense sources and extracting the pure essence of what you need to know.
Exactly. And today's a particularly interesting one, I got to say. We're looking at something that's, well, it's pretty cutting edge. You send over your notes, all notes 2020 12 3 29, catchy title, along with, let's see, Gemini Robotics Report.pdf.
Ah, yes, that report. Quite a deep dive, pun intended, into the world of AI and robotics. Specifically, Google DeepMind's, what is it, the Gemini Robotics family of models. It's some pretty groundbreaking stuff, really pushing the boundaries of what we thought was possible.
Right. And the way I see it, what you're really after is, well, you want the innovation, the big leaps forward. And look, I get it. We all want that quick understanding, that aha moment where it all clicks. So that's our mission today. We're gonna sift through all this material, this dense, detailed research, and we're gonna pull out the gold nuggets, the real gems of innovation.
And it's no easy feat, bridging the gap between AI as we see it in the digital world, the algorithms, the code, and bringing that into the physical world with actual robots interacting with, well, with stuff it's a huge challenge.
Right, a challenge that these Gemini robotics models seem to be tackling head on. Your material describes them as purposefully designed for robotics, built on top of Gemini 2.0, which, for those who might not be totally in the loop, is Google's well, one of their latest and greatest AI models. So we've got, let's see, Gemini Robotics-ER, and then just Gemini Robotics. What's the story with these two? What makes them so innovative?
Yeah, so let's start with Gemini Robotics-ER, and the ER here stands for embodied reasoning, and this is key, right? It's all about taking the reasoning power of a large language model like Gemini, and making it work in the real world, in the messy, complex, constantly changing real world.
Because it's one thing for an AI to process information, right? To understand language, to analyze images, things like that. But when you start talking about robots moving around, interacting with objects, with people, with their environment, it's a whole different ballgame.
Exactly. The digital world, it's all neat and tidy, predictable, but the real world, it's all about well, it's about space, about time, about physics, about understanding how things move and interact. And that's what Gemini Robotics-ER is designed to do. It's built to grasp those physical concepts, those real world constraints. It's like giving an intuition for how the physical world works.
Okay, so it's not just about seeing the world, right? It's about understanding the implications of what it's seeing. It's about knowing that if I push this cup, it might fall off the table. So how does it get this kind of understanding? What's the secret sauce?
Well, the real innovation here, the breakthrough, is that they've moved beyond just passive perception, right? Just seeing and recognizing. They've moved towards action, towards interaction. And your notes actually have a great definition of this. It's called embodied reasoning. And they define it as, let me see, the set of world knowledge that encompasses the fundamental concepts which are critical for operating and acting in an inherently physically embodied world.
It's a mouthful, but it makes sense, right? It's about having that knowledge of how the world works, how objects behave, and how actions have consequences.
Right. And these models, they're learning to not just observe, but to actually do things, to affect the environment and see what happens. To learn by doing, basically.
Which makes a lot of sense when you think about how humans learn, right? We learn by interacting with the world, by experimenting, by making mistakes and figuring things out. All right, so that's Gemini Robotics ER. Now, what about the other one? Just plain old Gemini Robotics. How did that fit into this whole picture?
Yeah, so Gemini Robotics, that's the vision language action model, the VLA model. It's like the action-oriented sibling to Gemini Robotics ER. If ER is about understanding the world, Gemini Robotics is about, well, it's about acting on that understanding.
It's about taking all that perception, all that reasoning, all that knowledge, and turning it into actual movement, into control.
Exactly. It takes those rich representations of the world and translates them into commands that can control a robot. It's the interface between the AI's mind, so to speak, and the robot's body.
And something that keeps coming up in your notes is this idea of a generalist model. And I think that's worth exploring a bit because traditionally, robots have been, well, they've been pretty specialized, right? You'd have a robot for welding, a robot for painting, a robot for assembling a specific part. But these Gemini robotics models seem to be, Well, they seem to be more adaptable, more flexible.
Right. And that's one of the really exciting innovations here, this idea of a generalist model that can handle, a wider range of tasks, that can adapt to different situations, even to different robot forms.
So instead of needing a different robot for every single job, you could potentially have one robot that can do, well, it can do a lot of different things.
And that's huge because it makes robots much more versatile, much more useful in real-world settings. Think about like a household robot, right? You wouldn't want a different robot to do the dishes, to vacuum, to fold laundry. You'd want one robot that could handle all of those things, that could adapt to new tasks as they come up.
That makes a lot of sense. Okay, so we've got these models. They're supposed to be really good at embodied reasoning. But how do you actually measure that? How do you know if an AI truly understands the physical world?
Well, that's where ERQA comes in. That's the embodied reasoning question answering benchmark. And it's a pretty clever way of testing a model's its grasp of, well, of the real world.
So instead of just, asking it to identify objects in an image, which a lot of AI models can do pretty well these days, ERQA goes a step further, right?
Exactly. It asks questions that require a deeper understanding. Questions about spatial relationships, about how objects interact, about the consequences of actions. And get this, right out of the box, Gemini 2.0, they aced it. Table 1 in the report, it shows just how well they performed on ERQA, state-of-the-art performance.
Which is pretty remarkable, right? I mean, these models, they weren't specifically trained for this. They weren't given a bunch of examples of ERQA questions and answers.
Nope. They were just, given the questions and they figured it out. And what's even more interesting is that they found that using chain of thought prompting, it really boosted performance.
Chain of thought or QOT. It's like asking the AI to think out loud, right? To explain its reason step by step.
Yeah, and you can see this in Table 2 and Figure 5. The improvement with COT-T is significant. And what this tells us is that, well, it tells us that these models aren't just, blindly matching patterns. They're actually engaging in a kind of logical reasoning. They're taking the visual information, they're processing it, they're thinking through the steps, and they're coming up with answers that show a real understanding of the physical world.
Okay, so we know that Gemini 2.0 has got this strong foundation in embodied reasoning. Let's dig a little deeper, shall we? Let's look at some of the specifics, the things it understands about the physical world. Your notes talk about let's see, 2D and 3D spatial concepts. So starting with 2D, what's new and exciting here?
Well, one of the big advancements in 2D spatial understanding is open world object detection. And you can see some examples of this in Figure 6. Basically, it means that these models can identify and locate a whole bunch of different objects without being limited to a specific set of predefined objects.
So it's not like those older systems where you had to train it on, I don't know, like 1,000 different types of objects and it could only recognize those specific objects.
Right. These models, they can generalize, they can understand descriptions of objects. They can even infer the presence of objects based on their attributes, like if you say something you can sit on, it might be able to figure out that you're talking about a chair even if it's never seen that particular chair before.
It's almost like it's building a conceptual understanding of objects, of what they are and how they're used.
Exactly. And that's a huge step forward for robotics because the real world is full of, well, it's full of surprises, full of things you haven't seen before. What else is there in 2D?
Let's see, precise pointing, figure 7 and table 3, they show some pretty impressive results there.
Ah, yes, pointing. That's a fundamental skill, right? For robots to interact with the world, they need to be able to, well, to point to things. And these models, they're not just pointing to objects as a whole, they're pointing to specific parts of objects, to areas where you might grasp something, to affordances, to free space.
To spatial relationships even, like if you say, point to the object to the left of the blue block, it can do that.
And what's really remarkable is that Gemini Robotics-ER, it actually outperforms a model that was specifically designed for pointing, called Momo. And you can see this in some of the benchmarks in Table 3.
So it's not just, good at pointing for a general purpose model, it's actually better than some of the specialists. Okay, so it can see objects, it can understand them, it can point to them, to specific parts of them. What about movement? Can it understand how things move in 2D?
Yeah, it shows some pretty interesting capabilities in trajectory prediction. Figure 8, it has some examples of that. So if you give it a description of a motion or an interaction, it can predict the 2D path that an object might take.
So it's not like full-blown motion planning where it's avoiding obstacles and navigating a complex environment, but it's a step in that direction, right? It's showing that it understands how things move, how they might interact.
Right. And on top of that, Gemini Robotics-ER, it introduces this top-down graph for prediction. You can see this in figure 9. And this is basically it's about predicting the best way to grasp an object from a bird's eye view.
Which is essential for a robot that's trying to, pick things up and manipulate them.
Exactly. Okay, so that's the 2D side of things. Now moving into 3D, that's where things get really, really interesting.
Yeah, 3D is obviously much more complex, much more challenging. So what are the big innovations in 3D spatial reasoning?
Well, one of the key advances is in multi-view correspondence, and this is all about understanding a 3D scene from multiple camera views. Figure 10, it shows how the model can identify corresponding points across different views and use that to build a 3D representation of the scene.
Which makes a lot of sense, right? I mean, in the real world, you're not just seeing things from one perspective. You're moving around, you're seeing things from different angles. And a robot, to really understand its environment, it needs to be able to integrate those different perspectives.
Exactly. And then there's 3D bounding box detection, and this is about locating objects in 3D space using just a single image, a monocular image. And this is where Gemini Robotics-ER, it really shines. Figure 11 and paper 4, they show that it achieves state-of-the-art performance on a benchmark called SUN-RGBD. And again, it's doing all of this in an open vocabulary manner.
So it's not just recognizing, a specific set of 3D objects that it's been trained on. It can generalize. It can understand descriptions of objects it's never seen before in 3D.
Right. And that's huge for real world applications where you can't always know in advance what kind of objects you're going to encounter.
Okay, so all of this spatial understanding is pretty impressive. But the real question is, how do you actually use this to control a robot? How do you get to do stuff in the real world?
Well, that's where things get really exciting. Your notes talk about zero shot and few shot robot control, and these are two really innovative approaches.
Yeah, zero shot, that's like the holy grail, right? Getting a robot to do something it's never been explicitly trained to do.
Right, and they've actually had some success with this using code generation. So Gemini 2.0, it's given access to an API, an application programming interface.
Which is basically a way for it to communicate with the robot to tell it what to do, right?
Exactly. And in this case, they were using the Alloa 2 bimanual robot. So Gemini 2.0, it could use this API to move the robot's grippers, to open and close them, to get information about the robot's state, about its perception of the environment. And then based on this information, it could generate code to control the robot.
So it's like it's writing its own little robot control program on the fly.
And you can see how this works in figure 12 and figure 34. It's an iterative process, right? The model, it takes in the visual information, the robot's state, it generates some code, it executes the code, it sees what happens, and then it replans. And check this out, right? Table 5, it shows the success rates on a bunch of different simulated tasks. And at Gemini Robotics-ER, in this zero-shot setting, it actually performs significantly better than the a baseline Gemini 2.0 Flash model. And table 6, it shows some real-world results. Not super complex tasks, but still it's able to get a robot to hand over a banana.
Which is pretty amazing when you think about it. I mean, this model, it's never been specifically programmed to hand over a banana. It's figured it out on its own based on its understanding of the world.
Right, and that's the power of zero-shot learning. Now, few-shot control, that's a slightly different approach.
Yeah, few shot is about giving the model a few examples, right? A few demonstrations of how to perform a task.
Exactly. And with few-shot control, they're using in-context learning, ICL. So instead of code generation, they're showing the model, maybe a handful of examples of how to do something. And these examples, they include the trajectories of the robot's end effectors. Figure 13 gives you a nice overview of this process.
So it's like showing the robot a few moves and then saying, "Okay, now you try."
And the really innovative thing here is that Gemini Robotics-ER, it can extract the relevant visual key points and object poses from these demonstrations on its own. It doesn't need, some other model to pre-process that information. And the results are are pretty impressive. Tables 5 and 6, they show that even just a few demonstrations can lead to big jump in performance.
Especially on those more complex tasks, those more dexterous tasks, the ones that require a lot of fine motor control. Okay, so that's using Gemini 2.0 for robot control. But then you've got this other model, Gemini Robotics, that's specifically designed for predicting robot actions. So how does that fit in? What's different about its approach?
Yeah, so Gemini Robotics, this is where they take things, a step further. Instead of relying on the general reasoning capabilities of a large language model, or just a few examples, they train this model on a massive data set of real robot actions. And these are teleoperated actions, meaning a human was controlling the robot, but they're recording all the data, all the movements, all the sensor readings.
So it's like showing the model a huge library of robot movements and saying, okay, learn from this, learn how to move, learn how to interact with the world.
Exactly, and they use this to fine-tune Gemini Robotics, and they've got this two-component architecture, which you can see in Figure 14. There's a cloud-based VLA backbone, which is derived from Gemini Robotics-ER, and then a local action decoder, which runs on the robot itself.
So it's got this combination of cloud-based intelligence and local control.
Right. And the results are, well, they're pretty remarkable. Figures 15 and 16, they show that Gemini Robotics, it can solve a lot of different manipulation tasks right out of the box without any specific fine-tuning for each individual task. And it performs really well on tasks with deformable objects, things like cloth, which have always been, really hard for robots to handle.
And it's not just about moving things around, right? It can also follow instructions.
Right. Figure 17, it shows how it can understand and execute pretty complex language commands, even with objects it's never seen before.
So it's got this combination of dexterity and language understanding, which is pretty impressive.
And one of the really big things they focused on is generalization. Because, in the real world, things are never exactly the same. You've got different lighting, different backgrounds, different objects, different ways of phrasing instructions, and they tested this quite rigorously.
Yeah, they tested it across three different dimensions: visual variations, instructional variations, and action variations. You can see all the different test conditions in figures 18, 19, and 20. It's pretty comprehensive.
And the results, which are shown in Figure 21 and Figure 40, they're really encouraging. Gemini Robotics, it consistently outperforms the baseline models across all these different types of variations.
And what's particularly impressive is that even in situations where other models just completely fail, Gemini Robotics, it still manages to function, to do something, to make some progress.
Exactly. It's robust. It's able to handle those unexpected situations, those curveballs that the real world throws at you.
Okay, so we've seen that it can generalize pretty well. But can you make it even better? Can you specialize it? Can you adapt it to specific tasks or situations?
Yeah, and that's another area where they've made some really interesting innovations. One of the things they looked at is long horizon dexterity. So they took Gemini Robotics and they firm tuned it on data sets for some really complex tasks, things like folding an origami fox, packing a lunchbox, playing a spelling board game, playing cards, even preparing a salad.
So they're taking this general purpose model and they're giving it a kind of specialized training, right?
And the results are pretty amazing. Figures 22 and 23, they show the success rates. And for some of these tasks, they're achieving, really high levels of success. The lunchbox packing task, they actually got 100% success.
Which is pretty incredible. I mean, that's a multi-step task. It takes over 2 minutes to complete, and they're able to get the robot to do it perfectly every time.
Right. And the key takeaway here is that the initial pre-training, the general purpose training on all those different robot actions, that's essential for enabling this kind of specialization.
It's like it's building a foundation of knowledge, a set of skills that it can then build upon, refine, and specialize for these more complex tasks.
Exactly. And they also looked at ways to enhance the core reasoning and generalization abilities themselves. So they fine-tuned Gemini Robotics using a relabeled data set that was designed to better align its action prediction with its embodied reasoning.
So they're basically refining its understanding of how actions work, of how they unfold over time.
Right. And figure 24, it shows how this reasoning enhanced version of Gemini Robotics, it performs much better on tasks that require, that require more reasoning, more understanding of the situation.
And figure 25, that's really interesting. It actually shows visualizations of the model's predicted action trajectories. It's like you can see the AI thinking, you can see it planning out its movements.
Right. And then they also explored this idea of rapid adaptation. So can you take the model and quickly adapt it to new tasks using just a small number of demonstrations?
And the answer seems to be yes.
Yeah, 2026, it shows that they were able to get the model to learn new tasks with a few of 100 demonstrations. And for a lot of these tasks, they were getting, success rates above 70%. So it's pretty adaptable, it's pretty quick to learn.
And this all leads to the really exciting possibility of using these models to control, well, to control different types of robots, not just the specific robots they were trained on.
Right. And they did some preliminary experiments with this, adapting Gemini robotics to control a bi-arm Franco robot and even the Apollo humanoid. You can see these robots in figure 27.
So they're taking this model that was trained on one type of robot, and they're saying, okay, now go control this completely different robot.
And the results shown in figure 28 and figure 47, they're pretty promising. The model, it's able to adapt to learn how to control these new robots, and it even seems to retain some of its generalization abilities.
So it's not just, learning the specifics of how to move the arms and legs of this new robot. It's also keeping some of that general intelligence, that ability to handle new situations, new objects, new instructions.
Right, and that's a big deal because it means that we might be able to develop these truly general purpose robot control systems that can be adapted to all sorts of different robots.
All right, so that's all very impressive, very exciting. But there's one big question that we can't ignore, and that's safety. Because when you're talking about robots that can learn, that can adapt, that can act autonomously, safety is paramount.
Absolutely. And they're very aware of this. They've taken a multi-layered approach to safety. So they're interfacing with lower level controllers that handle, those critical safety functions. They're also focusing on what we call semantic action safety, which is about making sure that the actions that the AI commands, that they don't violate any safety constraints.
It's not just about the robot itself being safe, it's about the robot's actions being safe, right?
Exactly. And to evaluate this, they've developed these data sets, the Asimov multimodal and injury data sets. You can see some examples in figures 29A and 29B. And they're using these data sets to test the models to see how well they understand, what's safe and what's not safe.
And the results, as shown in figures 29C and 29D, are pretty encouraging. Even the earlier models like Gemini 2.0 Flash and Gemini Robotics-ER, they already show a pretty good grasp of physical safety. They can recognize potentially dangerous situations. They can understand the consequences of certain actions.
Right. And on top of that, they're using techniques like constitutional AI, which is basically about embedding ethical principles, safety principles into the AI itself. So that even if someone tries to give it a harmful or biased prompt, it's very likely to reject it.
So they're building safety into the AI from the ground up.
Exactly. Okay. So we've covered a lot of ground here, but obviously there's still work to be done. There's still, limitations, there's still challenges.
Yeah, no technology is perfect, right? So what are some of the areas where they see room for improvement?
Well, one area is in embodied reasoning. Specifically, they want to improve the model's ability to understand spatial relationships in longer video sequences, and also to make more precise numerical predictions for tasks that require, very fine-grained control.
So it's about getting even better at understanding and predicting how things will move and interact in complex dynamic environments.
Right. And they also want to push the boundaries of generalization even further, to handle even more complex scenarios, even more diverse environments.
And of course, the ultimate goal is to achieve zero-shot cross-embodiment transfer, which means being able to take a model and have it control any robot without any specific training on that particular robot.
Right. That's the dream, right? To have these truly general purpose robot control systems, and they're making progress towards that.
All right, so to sum up, the Gemini robotics family, it represents a pretty significant step forward in bringing AI into the physical world. The innovations in the model architectures, the training techniques, the capabilities they've demonstrated in manipulation and generalization and adaptation, in safety, it's all pretty remarkable.
It really is. And for you, the listener, what's exciting is the potential of this technology. Imagine the impact this could have on all sorts of industries: manufacturing, logistics, healthcare, even just everyday life in our homes.
Yeah, as these intelligent, versatile robots become more common, more capable, it's gonna change things. It's gonna change the way we live, the way we work, the way we interact with the world.
And that's something worth thinking about.
Right. So as we wrap up this deep dive, I want to leave you with this. How do you think these advancements in robotics, how do you think they're going to shape the future? What new possibilities do they open up? What new questions do they raise? And specifically, what applications of this technology, what applications of these general purpose robots do you find most compelling, most transformative? Thanks for joining us.